All modern computers use pipelining to execute instructions more efficiently. Suppose there is an instruction which produces a value to a register and another instruction which reads that value. Then we have a true data dependence from the producer to the consumer. There is also data dependence if we have two instructions which both write to the same register. This is called output dependence. And if we first have an instruction which reads a register and another subsequent instruction which overwrites it, there is an anti-dependence. Given a basic block, what we can do is to optimize the program to make it faster, is to rearrange the instructions without violating the data dependencies. And we can do that using by creating a data dependence graph. That's a graph of instructions. The instructions are the nodes and these dependencies are the edges. It's a directed graph, and we can perform a topological sort on this graph. And if we do that in a very clever way, then we can make the program faster. This is, for all realistic machines, an NP-complete problem. So we have to use heuristics, obviously. Unfortunately, list scheduling is not very efficient for short loops. If we look at this loop, where we have, and we can assume these are floating point instructions, with only 3 instructions, and if we assume that A produces a value to B, which produces a value to C, then we cannot rearrange it. What we can do, however, well, if there is no data dependence between iterations which prevent us from doing so, but if there is none, then we can execute multiple iterations at the same time. So instead of only doing first A, then B, and then C, we can take one instruction from one iteration, another instruction from a later iteration, etc. In this case, we run 3 iterations at the same time. For that, we also need a prologue to start up this and an epilogue to finish. For instance, here we do one A from this column, and then we need to finish that. And also a C operation from this column. If there are no dependencies between the iterations, then we can do this and essentially avoid the pipeline stalls. So how can we do this? Well, there are 2 limitations. The first is data dependencies, which may prevent, suppose there is a value is needed in the next iteration, then of course we cannot run the instructions in the wrong order. And secondly, the second limitation is hardware resources. There must be sufficient hardware resources for each clock cycle, otherwise there will be pipeline stalls anyway. If we have unlimited hardware resources and no data dependencies between iterations, then we can run all iterations at the same time, but that's quite uncommon. So what we want to do is to use list scheduling and try to start the next iteration as early as possible without violating hardware limitations and data dependence limitations. This was invented in the late 1980s by a PhD student from Carnegie Mellon University, Monica Lam. There are other approaches to this general optimization of executing multiple iterations at the same time, which is called software pipelining. But modular scheduling, her algorithm, is actually the best. And this is very important for for floating point programs.